Hello, so my name is Lev, and I'll talk about how to find the text similarity you want using the next generation of word embeddings in Gensim. This is my first talk as not a maintainer of Gensim. We have a new maintainer now called Ivan. I'm just a contributor right now. So my first slide was supposed to convince you that Gensim is an awesome library, but I think Robert has just done a very good job of it in the previous talk, where he used Gensim doc2vec to analyze comments. So this is kind of redundant, but I'll tell a couple of words. Gensim is an open source package. We have word2vec, doc2vec, topic modeling. It's been around for about 8 years. Check us out on GitHub. We are at this intersection of academia and industry. So we have a lot of industry adopters, a lot of big and small companies use our code, from Amazon to small startups. And at the same time, a lot of people in academia use our code as well. We have about 500 academic citations. And generally, we take academic code, which is written in C or C++. The variables are called gamma, alpha, beta. There are no comments there. It kind of takes, you have to download, build protobufs from scratch to compile it. It's like, this is what the code starts with. And we turn it into some Python code, which has comments, which has continuous integration, which is maintainable, something you can put in production and be confident about. That's what the mission of Gensim is. Take some academic code and make it into industrial code. And we've been doing it for about 6 years. Cool. So who here has used Gensim before? Okay, more than half the room. Awesome. And hopefully the rest of you will try it out after today's talk. So credits for today's talk. Most of the things I'm going to talk about has been done by Parul. Parul is our current Google Summer of Code student. I talk to her every day for this entire 3 months this summer. And she done most of the code here. And most of the new features in Gensim are done by students. This is our incubator program, some recent students. Some of you have been to a tutorial on Friday run by Bhargav, who is a graduate of our incubator program. So if you're working on a master's thesis, or you're just a student or thinking of transition to data science, talk to me, and we'll offer this free internships where you contribute to open source and learn something about NLP. So just talk to me after this, find me after this talk. If you're interested in this. Okay, so let's move to the main, topic of this talk. In Robert's talks, you've just seen, how he finds similar words to, Brexit and, woman and king. And sometimes words come out similar, sometimes they come out not so similar. So let's talk about which words are similar for a while. So these two words, coast and shore, are they similar or not? So if you think they're similar, raise your hand. So I have 1, 2, 3. Okay, most of you think they're similar. Why do you think that they're similar? Somebody just tell me. Huh? The synonyms. Okay, so they have the same meaning. So I can say I'm walking on the coast, and I can say I'm walking on the shore. They have the same meaning in the sentence, right? Depends how you define words. Oh man. Tokenization is quite hard. In Chinese, you don't even know where the word boundaries are. Okay. Yeah, what is a word? Yeah, what is the meaning of a word? You have to define what the word is. That's even one way deeper. Let's just state we all sort of understand what words are. Let's just talk about the meaning of words. Okay, so coast and shore, they're similar. Most of us agree. What about close and closet? Are they the same or not? Okay, if they're similar, raise your hand. Okay, only 4 or 5 of you think that they're similar, and the rest of you think probably they're not similar. Yeah, I agree that they're similar with you in the sense related. They're on the same topic of what people wear. I take my clothes from the closet, they always appear in the same context. They're definitely friends. They're from the same, ballpark. So they are definitely related. And of course they're different. I put on my clothes, I can say that. I put on my closet, that doesn't make any sense. So they're definitely not interchangeable, but they are related. So they're similar words, but what does similar really mean? That is, so these are 2 different notions of similarity. You can find, invent your own notions of similarity as much as you want. And for your business problem, it might be something special for you. Okay. And so they're different because they're not interchangeable. And there are some specific business problems where it matters which words are similar and which words are different. And we're going to talk about these two business problems today. And first one is, what does Elizabeth think about Mr. Darcy? And the second one, what about the male characters in Pride and Prejudice? Like, how of you have read Pride and Prejudice or like saw the movie or something? Just as a familiar context. Okay, third of the room. Yeah, I tried to find some German novel, but the German novels are very short. There's like, like Sorrows of Werther is 1/3 the length of Pride and Prejudice. And like, Franz Kafka's Trial is like 1/5. So like, it's impossible to train models on them, unfortunately. German novels are too short. So I couldn't find a good reference. I have to use English language in Berlin, I'm sorry for that. So these are joke problems, but they translate into real business problems. And the first business problem that you can actually solve is what words are in the topic of Darcy? What words are in the topic of bad customer service complaints for my company? And these are just general topical words. Clothes and closet will be in the same topic if you're solving problem number one. But if you're solving a different problem, if you just want to find all the named entities in the text, then you actually care about what words are interchangeable with Darcy. Because all the males in this 19th century novel, they do the same kind of actions. And you'll find that they actually quite interchangeable words. So similar words are different in the context of your business problem. So for first problem, it will be attributes or relatedness. For second problem, it will be interchangeability. So the second problem, it will be coast and shore should be related, should be similar. Okay, so let's run some code now. So there's a notebook that you can see on GitHub. This is the short URL for that. Yep. So let me show some code, just to see. So like first okay, this is readable. Cool. So you can get the text of Pride and Prejudice for free from Project Gutenberg. Just download it, then you read it, and you pre-process it with spacing. Like previously, you talked about questions to Robert were about lemmatization, and this is just in space. It's so easy. You just do it one line, and that's NLP, parenthesis text, and it does all the pre-processing for you in some way. And you can see there are 6,000 sentences in Pride and Prejudice, and there's about 120,000 words in there. Like it's kind of small corpus, like you need 500,000 words to make any word embeddings to work, but you can still get something. Werther is 40,000 words, and that doesn't work at all. So at least 120,000 words, we can at least get some foothold and see what's happening. Like for comparison, English Wikipedia is 17 million words, and that's really nice models. So above 1 million, you get very nice models. But let's see what we can get 120,000 words. So yeah, we just import Gensim word2vec. And have a look at our processed sentences. So, like this is example of a processed sentence. Let's fit it on the screen. So this is what it looks like after lemmatization and processing. So this is just a disclaimer of Project Gutenberg. And you see a lot of things have been removed. For example, some things have been removed, punctuation marks have been removed, and this is what it looks like after pre-processing. So this is one model I'm going to train, and it will be a model that predicts interchangeable words. Like coast and shore will be similar in this model. And this is just one line in Gensim word2vec, takes some seconds to run, and I want to see what is this most similar words here to Darcy. And for those of you who have not read Pride and Prejudice has been written as a first-person novel. It's written from the point of view of Elizabeth. And at some point, there's two men who are both interested in Elizabeth, Darcy and Wickham. And this Mr. Wickham comes up as the first most similar word to Darcy, in interchangeable words. So they are in some sense interchangeable, like they do similar things. And all the other male characters are in this list. Mr. Bingley, Collins, Gardner, they come out this way. Yeah, like I apologize for using male characters. It's harder to use female characters because of first person thing. Like Elizabeth says I or me, and it's like hard to distinguish between when she says I or somebody in the dialogue says I. So female characters are much more complicated in this book. So that's why I had to use male characters. So yep, these are the male characters in the book, and you just get them by training this model. Yep. Let's train a different model, and I'll call it attributes of model. So this also takes some seconds to run, and the results that I get attributes of Mr. Darcy. First guy that comes up is Bingley. He's his sidekick, And then there are different actions that Mr. Darcy does. Like, he's very silent, aloof, sometimes he smiles, and experiences astonishment. So this is just things which are in the topic of Mr. Darcy. And say, imagine if you're analyzing customer complaints, if you look at bad service, you'll see all the words which are in the topic of bad service, if you use these attributes of model. But if you use the interchangeable model, you would see just, bad service be similar to, rude, rude waiter. Like things which are quite interchangeable with that. Cool. Okay, let's go back to the slides. List of words. Cool. Yeah. And the parameter that I changed here is called the window parameter. And this, the difference between these two models is just this window parameter. And window parameter defines when two words are together. So if I set my window parameter to 2, then I just only go left 2 and right 2 of my word. So if I see Darcy, I just go left, right, and 2 right, and these are all the friends of Darcy that I've encountered. And the more frequently I see these words together, the more similar they become. And for the attributes of model, I use the window of 50. So I basically take my entire sentence, and they all become friends of Darcy. And so I can see more broad differences here. Just because I look at the wider context of the word, and that's how I get the wider topic. Not just the things that Darcy does, but more like places where he goes and different attributes of him. So there's just one parameter called window. And this is an evaluation of these models on some pre-annotated data sets. So in academia, people think a lot about this two kinds of similarity, interchangeable and related analogies. Like interchangeable I just described, related is when they're in the same topic. And there are several data sets that you can use. Just download them and see how well your model does on these two kinds of analogies. And you see that like small window equals 2, does better in interchangeable ones, and the window equals 50 does better at related ones. And window 15 is sort of does well in both, somewhere in the middle. When you are doing your own commercial models, you actually have to create this data set from yourself. Like if I'm doing customer complaints, I have to create myself this little table where I say that bad customer service and rude should be similar, and some other words should be different. But I encourage you to create your own just little table of things that you want to be similar and things you want to be different. And that way you can validate your model. For example, yesterday, if some of you were in Miroslav's talk, he was telling you he was showing an example of when word-to-vec works and when word-to-vec doesn't work. And what does it mean word-to-vec works or doesn't work? It works for one interchangeable words, but doesn't work for related words. So you have to create your own data set of things what you define as works, and then you can evaluate on that and see how well it's doing. So that's the solution to that. There are no, unfortunately, good manually marked data sets for customer complaints, because they all come from academia and they only think about some fundamental, linguistic things like interchangeable words, semantically related words, this kind of things. But I haven't seen any good industry data sets here. But you should create your own for your own task, and then you'll know if your model is working or not. In that way. Cool. So that was about the window size. Do you have any questions about it so far? OK, we'll have more examples and questions in the end. So the window size is one hyperparameter. Another hyperparameter is just which algorithm to use. I'll talk more about the theory of them in the next 10 minutes. But this is just to show you the differences. I have the same window size of 15, and I train 3 different algorithms. And they all give me word embeddings. But I get different results, like same data in, but different results out. And there's 3 algorithms, like word rank gives you attributes, word2vec gives you interchangeable stuff, and fastText gives you a mix of both with the same window. How many of you have heard about fastText here? OK, half the room. OK. What about word rank? Yeah, word rank is really cool. OK, 1, 2, 3, 4. Usually nobody has heard of word rank. That seems like the point of this talk is deliver word rank to people. It's an awesome algorithm. I'll talk more about this theory later. Cool. So you see same stuff in, but different algorithms give you different results. Let's talk more about the, actually let's run fastText on our Pride and Prejudice stuff. So this is a Gensim API for fastText. It looks exactly the same as for word2vec. You don't need to do anything new. fastText is this library which is released by Facebook AI Research in August. It's written in C++. It's kind of it's like not so simple to compile. But it's available in Gensim Docker container. You can just get Gensim Docker container of all that stuff, and you can use fastText without any compilation problems. And it also has a Python API now from Gensim. It's right now just a wrapper, but by the end of the summer, there's a G6 unit working on a Python Siphon implementation of it, which should be just native in Python of fastText, so it should be easier to use from then on. Cool. Rather than using some C++ library. And so this is just same data coming into fastText, and I should get different results. Okay, let's wait for it to finish in a little while. No. Yeah, it's not so fast. It's actually slower than Word2Vec. Yeah, and because I'll tell you why in a second. But it's definitely slower than Word2Vec. There's nothing fast about it. Yeah, you can see it already. Even though it's written in C++, and Python is supposed to be slow and lazy. Okay, cool. So these are our stuff. So the changeable words with Darcy. So I have different versions of Bennett and Bingley and Gardner's and victims. So this is kind of sort of similar to that, but I have Bennett's and Bennett as two different things, and Gardner's and Gardner and Collins. So it's kind of I still get male characters, but it looks different. And for the attributes, I get. Well, just ask for a longer one. But the attributes, I think, are slightly more meaningful here. It's much better at the attributes than the Word2Vec. So you can see, yeah, this is for Darcy. So yeah, dwell or dare. So it is to me it seems more descriptive of Mr. Darcy's aloof personality and how he has to overcome his pride in this novel. There's another guy in the novel called Wickham, who is not such a positive character, and you can see that his attributes are, yeah, his attributes should be more negative than that. Yep, you can see drink, and there should be conceal in here sometimes. Yeah, okay. That one doesn't. Yeah, okay. Maybe this random seed doesn't look so good. Yeah, on the 120,000 words, it's very hard to get something meaningful out of it. Yeah, some random seeds give you something good, some random seeds don't give you something so nice. Cool, but just see that you have different results for the same input, different data sets. Okay, let's go more into the theory of word embeddings. So this is probably going to be the third time this slide appears in the PyData conference, Berlin 2017. You have seen it in Barbara Plank's keynote. This is, definition of word embeddings. Who has seen this definition before? Okay, so I can just, I'll talk about it very quickly. So if I have a vocabulary of 1,000 words, and I want to find a vector for every word, what's the easiest way to find a vector for every word? You just have one hot representation. The word number 1 will have this vector which is 1,000 long. Everything is a 0 except the first bit. The first bit is just turned on. I have 1. My second word is king, so I'll turn on my second bit. It'll be 0, 1, 0, 0, 0. The third word is book. It'll be 0, 0, 1, and the rest of them are zeros. So this is one way to represent words. I just have a vector for every word. The problem is that the vectors are very long. They're 1,000 long. Most of the stuff is 0. And the most important problem with this is I don't see a relationship between king and queen. King and queen are related, more related than the king and book. And I don't see that here at all. King and queen, king has 1 in the first column, queen has in the second, book has in the third. There's no relationship information encoded here. And what Word2Vec and all these word embedding algorithms do, they create a distributed representation. It's where I have much less dimensions, maybe 3 or 100, not 1,000, much smaller vectors, and the meaning is distributed across all the dimensions here. King is no longer stuck in the first column, it's distributed across all 3. So I have 0.94 and different floats in my different dimensions. So the meaning is distributed. That's why it's called distributed representation. Or you can call it a word vector or a word embedding. It all means the same thing. And it's a low-dimensional vector space. The problem is how do I come up with these numbers? And for them to have some kind of meaning. And that's the theory of word2vec. So this is an example of a model trained on Wikipedia, and you have the word king, and it's in 100 dimensions, and then it's projected down to 3D using some PCA, I think, in this case. So you can see like king is in the middle, and then you can see regicide, and kind of things related to king somewhere in the middle. So, I mean, some people can tell how good the model is by looking at this. I don't know. I cannot really tell what happens by these things because it's PCA from 100 dimensions into something small, and the words which are close together should stay close together according to PCA intuition. Words that are far away, like who knows what happens to them on the PCA? That's not guaranteed. And you know, if you've been to Matti Lira's talks yesterday, he was talking about how to evaluate this kind of unsupervised learning models. You know, if it's unsupervised, there's no goal. How do I know if it's good or bad? So, you know, that's what he said yesterday, that projections are meaningless, you know, like, that's, okay, so this is, like this visualization is done in TensorBoard. TensorBoard is a really cool library, you know, it's part of TensorFlow visualization package. And yeah, you can do this, just bring them to client meetings and like show it to a client that you use this fancy model to do it. But for actually understanding your models, just do this tables that I showed you, like Gensim, you know, most similar call, and you'll see the numbers, you'll see it in like in a very good way, you know. But just, yeah, don't really talk about this projection stuff that much. Cool. So let's go more into the theory. So how to come up with these vectors. Like, you know, they're floating here in the space, but like, I have this, you know, 0.94, 0.57, 0.22, like, why this number is selected? Like, what's so good about them? I could just, there's, you know, infinitely possibilities for them. So how to come up with these vectors for king? And we'll start with our, you know, corpus. Corpus is just an NLP, like, you know, word for data set. Like, if you're an NLP person, you say corpus. If you're a general data scientist, you know, like vanilla one, you say data set. But, you know, we'll say corpus. Don't know why. So this is, we have only 4 sentences in our corpus. They're about cats, because cats are the thing. And one about dogs, just, you know, for diversity. So we have, you know, cute kitten purred, cute furry cat purred and meowed. And this is like picture of a cat. This is me, you know, working in my, you know, it is my friend's cat. I work remotely, so sometimes I go to my friends' places who also work remotely, and we work together for this like co-working dates. It's like a strange idea of having a work date, and you just sit in the room and don't talk to each other and, you know, work. Yeah, if you go to Matti's house, he has a spare desk in his office for just co-working guests. This is amazing, you know. This is like amazing Berlin living, having a desk in your office for co-working dates. This is, you know, amazing city, and nowhere else I've seen this. Okay, cool. This is our corpus about cats. Let's extract some information out of it. So I'll find out which words are friends, like which words appear in the same context. So kitten has context words of cute and purred and meowed, and cat has the words of, you know, cute, furry, and meowed, and dog is, you know, loud, furry, ran and bit. So, okay. Let's make it into a matrix. So kitten and cute appear twice together, and kitten and furry appear 0 times together, and, you know, kitten and bit appear 0 times together too. So that's a co-occurrence matrix. That's already a really good matrix. If I look at the row for kitten and row for cat, they're pretty similar. Like, you know, they have the same, they have both numbers in the first dimension. So that's awesome. Yep, and I can already see the kitten and cat is similar, and dog is different from them. But the only problem with this matrix is that it's, you know, 10,000 by 10,000. It might have 10,000 words in my vocabulary and have 10,000, you know, context words. That's the only problem with it. It's really big. It's really informative, but it's just too big to do anything meaningful with it. Yeah, that's the only problem with it. So let's do dimensionality reduction. Let's make it smaller. Just let's factorize it into 2 small matrices. So I have vocab by vocab, and it becomes vocab times something small by vocab. And the first row in the U matrix is just something that describes kitten. Some, you know, hidden meaning of kitten will be in that matrix, and that will be, you know, maybe 100 long. Not 10,000, but just like 100 long. That's how I get my word embeddings. That's basically what all of them really do. Yeah, like there's some caveats here if you want to read, like if you read my theory, it's not exactly like that, but that's enough intuition for the first approximation of word embeddings. That's how it happens. Okay. The 3x4 is different from 3x4 on my laptop. Yeah, sorry about the problem with the slides. If I have a vector for a word, and I have a vector for a context, and I do that dot product, what I should get is the co-occurrence count. Like, I have a kitten and cute appear twice, so the dot product of these two vectors should be higher than the dot product of cat and cute. Because cat and cute only appear once, they should have small dot product, and kitten and cute, these two vectors should have a high dot product. So that's all I'm trying to do, is just approximating this dot product with I want my co-occurrence count to be equal to the dot product of these two vectors. And that's how word2vec works. And that's the same as a similarity. The same thing is for similarity of two vectors. Here my kitten and cute will be more similar than cat and cute, because they appear more times together, so they'll be more similar in the same context. So the similarity is basically the same as co-occurrence in this word2vec world. You can think about it that way. In the fast text world, things are different. The similarity there is not just the co-occurrence of words together, it actually goes deeper and goes into subwords. So if I look at the word going, it's split into many different parts. It becomes the geo, oi, in. I look at all the two character chunks of that, and the three character chunks of it as well. And then I want to see the similarity of going and cat. I look at all the little chunks of cat and all the chunks of going and how often the two appear together, and sum up over all of them. So like I'll have see ka and go, k and ing, at and ing, and I'll go deeper into subwords. I mean, and it's kind of nice because I can see that going and go will be similar because they'll have the same word, geo and geo. And it definitely has some meaning in it. So let's run some code which shows that. So, for example, the word night appears in Pride and Prejudice, but the word night doesn't appear there because I did lemmatization. So Spacey took nights and changed it into night for me, just to make my life easier. So this model has never seen the word nights. But actually, the things that they're very similar. Even though it's never seen the word nights, it can still see that they share a lot of subwords together, and therefore they should be similar. The funny thing here is that I also think that night is something that's never seen before, like the guy who rides a horse and armor. And for a night, it also thinks that night and night are very similar, like 99.9% similar, because they only differ in one word, in one character. And it just looks at the subwords and finds a lot of similar subwords in them. And model unfortunately never had a chance to learn meaning of night. The only way it could have learned it is by seeing it used in a lot of examples. And Jane Austen never used the word night in her novel, unfortunately. So the model never had a chance to use it, and it's just confused. It thinks that the word night is related to night, and that's a problem if you look at the subwords. And this thing of looking at chunks of words, that's really like a poor man's morphology. Like normally I would get a trained linguist who will tell me this is the root, this is the ending, this is this bit, this is that bit, and create some kind of rules for me to split the words into chunks. And if I cannot do that, I just do it in a hacky way. I just try all the different combinations, try all the different subchunks, see what's more important, and maybe that will help me in some way. And it actually works really well. Yep. So it works really well, but it's also slower. And the reason it's slower is because I have much more vectors in my vocabulary. Instead of having one word going, I have the word go, have the word ing, and I have the oin in there. So it's just, my vocabulary is much bigger, and I have to consider much more candidates. That's why fast text is slower than anything else. They should call it slow text, maybe. I don't know. Yeah, but it behaves much better for interchangeable words, because the interchangeable words usually have some parts of the word shared between them, like going and go. They're quite interchangeable. So that's looking at the subwords really hacks the interchangeable problem really well. So you can see how for interchangeable words accuracy, fast text blows everything out of the water. You can see like this big, orange spike here. Cool. Yeah, you already seen the API. For fast text, it's the same as for anything else in word2vec. And fast text is actually slower than the Python word2vec, even if you don't look at the word chunks. If you say it, only look at the word chunks of maximum length 0. So just don't look at the word chunks at all. And then it should do the same thing as Python word2vec. And the C++ code should really beat Python, but it doesn't. So, it's a PyData, so, I just wanted to show you that Python is quite fast and performant. I mean, of course, it uses Cython underneath, which is the C, but, it's still Python. Okay, cool. And there are many ways to get vector for word. I showed you word2vec, fasttext, and wordrank. You can just take this co-occurrence matrix with kitten and furry and factorize it in simple SVD. You can try glove, eigenwords, var embed. There are many different ways to find the word embedding. Just try different things, see what works for you in many ways. Okay, cool. Let's move to wordrank. So wordrank is this word embedding, which is a couple of years old. And this is quite nice. It has a different formulation of a problem. In word2vec, it's a classification problem where I have an input context cute, and I want to see what's the best friend of cute, and it comes up with kitten. So I just have to predict, one word out. In wordrank, it's a different problem. So I have my context coming in as cute, and I want to see rank me all the friends of cute. Rank all the words and how friendly they are towards cute. And the first one is going to be same as kitten, but the second one is going to be cat, and the third one is going to be dog, because dog and cute never appear together, because dogs are not cute. And and kitten and cat was cute once, and kitten was cute twice. So that's why they rank this way. But you have to create the whole ranking, and there's even a cost matrix here, cost metric here. So a mistake at the top costs you much more than mistake at the bottom. And when I look at more similar, how do you use word embedding models? You only normally use them as where is it? This way. I just do Gensim or similar, and what I care about is the ranking. That's really how they're used. And wordrank directly predicts that thing for me. That's the goal of wordrank, is to give me the top 10 very well and not care about the rest of them. Word2vec just cares about the top one. And wordrank actually does what I usually use the word embeddings for. Cool. So this is the difference between wordrank and word2vec. And it does, we have a wrapper on wordrank. The API is the same as word2vec. You can easily switch your models in production just to see which works better for you. That is a library in C++, which has many dependencies, but just get the Docker container and it'll work. Yeah, so you don't have to install some numeric libraries. Cool. The only problem with wordrank, it takes forever to run, because it's a much harder problem. You're not just predicting one point, you're predicting the whole ranking, and it's something that takes 18 seconds to run. Word2vec takes 18 seconds to run a million words. Fasttext is 50 seconds. You're all bored waiting for fasttext 10 minutes ago. In wordrank, I'm not going to train wordrank today. It takes a really long time to train. That's the only problem with it. It takes 4 hours to train, but it works really well if you have little data and you want to find this related accuracy between relationship between close and closet. That works really well for that. This is some test results, even on a small data. So this is the table on what you should use and when. So if you want your similar words to be related, like why related, like clothes and closet, if you want to describe just the topic, and you want to know what the document is about, then you should run wordrank. And even a small corpus, 1 million words is a very small corpus, and wordrank on 1 million words worked just as well as word2vec on 5 million words, and for this specific related task. So it's really good for that. It's quite noise resistant because it does the ranking. And yeah, has anyone used learning to rank before for anything? There's a whole world of machine learning where just do learning to rank. Okay, there's one person heard about learning to rank. I haven't heard about it until I encountered wordrank. So it was discovery that this whole thing exists, and it's actually much more noise resistant than predicting a point. Predicting the whole ranking is more fun sometimes. Cool. And another problem is if you want to recognize names in your text, and you just care about the function of the word and what things it can be interchanged with, then you should use word2vec of a small window, or fasttext of a small window, and a small window equals 2. And that's if you want to get different similarity, interchangeable words. And this is the same thing, but in a flow diagram, just as not a table, but as a flow diagram. So my similar words are related, go left, my similar words are interchangeable, then I should go to fasttext, word2vec, and var embed. If you got 1 million words, use word2vec. If you have got less than 1 million words, use wordrank. Yeah, this is the gist of the talk, basically, of this next generation of word embeddings, which are there just beyond Word2Vec, something else you can try, and you should try. Cool. Yeah, thanks for listening. This is all from me. You can find me on Twitter. Cool. Yeah. I think there's one on there.
Nice talk. And I'm curious about double meaning words. So let's say can as a container and can as a verb. How it affects these word embeddings, and do we have a way to identify them through their embedding?
Yep. So that definitely ways to do it. That different algorithms which you can try. The simplest thing that you can try is if you use spaCy for preprocessing, it can also tell you which part of speech it is, if it's a noun or a verb. And that way you just have can/nn or can/vb. You just put them into your model as like two different strings. You just have a string called can/nn and can/vb. And you get two different embeddings for them. So that's the easiest way to do it in using spaCy. Problem, it takes slightly longer to pre-process it because you have to do this parsing, but spaCy is pretty fast. That's the easiest way to solve it. There are a lot of academic papers about it, but in commercial consulting, somehow it hasn't really come up as a problem. Like if you look at just insurance text, usually the words have the words have only one meaning there because it's kind of specific domain, and there we never really had to use it, this kind of tricks. But it is a good question to ask. Thank you.
Hi, thank you for the talk. One question, in your experience, compared to fast text and WordRank and Word2Vec, how does GloVe do?
Yep, GloVe does pretty well. The only problem with it that how it's implemented. Example, in Python, there's no performant implementation of GloVe in Python. And the reason for that is you have to start with the whole concurrence matrix at once. Like you have to take your corpus and process it, and you have to have 10,000 by 10,000 metrics, and you have to create it and store it in memory. And that's, if your vocabulary is large, it takes a little while, and you have to go through the whole corpus before you can even start doing GloVe. Word2Vec does it in a streaming manner, so you don't have to have this whole thing, don't have to see the whole corpus at once. You can just stream things through, and it implicitly constructs this co-occurrence matrix just by streaming it through. That's the engineering aspect of GloVe makes it hard to use in production. That's the problem with it. But yeah, GloVe is working quite well. Yeah, there's not much difference between GloVe and Word2Vec. It just has a better formula. It's much more explicit. It's a nicer paper to read as well. In academic conferences, people talk about GloVe and talk about word embedding. In the industrial complex, they talk about Word2Vec when they say word embeddings. It's just a matter of environment.
If I'm working on a huge corpus, and if I'm fiddling with the parameters such as number of dimensions for the vector and the context window size, of course, it takes a lot of time to train for the huge corpus. So should I try it, or is there kind of an optimistic kind of values, or is there a relation between the length of the sentence and the dimensionality of the vector to be used? Okay, so there are two hyperparameters that you can do, like the dimension of the model and the window size. So the window size is more about the meaning that you capture. So once you do more similar, you can already see what the model thinks is more similar. If you get names, then your window size is small. If you get too vague things, then the window size is too big. You just get it from looking at similar words. The dimension size is different. Dimension size is a usual, overfitting, underfitting, just general machine learning model thing. Like the bigger, more dimensions you are, the easier it is for you to overfit on the training set, and have bad performance on the test.
So if you have accuracy on your training is 99 and on your test set it's 50, then it means your dimension is too big. So that's how you tune the dimension parameter.
So I need to try it out personally with the test cases, and then I need to change it again.
Yeah, but heuristics are different. For window size, you have one heuristic just looking at list of most similar words, and for dimension size, you have different heuristic by looking at train and test set performance.
Okay.
Yeah.
Is there any other question? If not, let's thank our speaker.
Thank you.